One of the most beautiful, most profound achievements in all of science, Albert Einstein's field equations. Let's get to it.
I mean, just think about that for a second. How is it possible that one single mathematical idea can explain a falling apple here on Earth, the orbits of planets, the way starlight bends across the universe, and even the expansion of the cosmos itself? Well, that's the incredible power we're going to unpack right now.
So here's our game plan. First, we'll dive into the revolutionary idea behind it all. Then we'll stare the equation right in the face and break it down, looking at one side that describes the shape of space-time and then the other side that reveals what's actually causing it to curve. And finally, we'll see how these two sides are locked in a kind of constant cosmic conversation.
Okay, first things first. To really get what Einstein was doing, you have to completely rewire your brain about gravity. Forget everything you thought you knew. It's not some mysterious force pulling things around. It's something way, way cooler. It's built into the very fabric of reality.
For hundreds of years, right, we pictured gravity as this invisible rope, kind of yanking things toward each other. But Einstein's general relativity just shreds that idea to pieces. It says that big things like planets and stars don't pull on other objects, not at all. Instead, they literally bend and warp the four-dimensional fabric of space-time around them. So what we feel as gravity is just us moving along these curves, following the contours of the universe.
And it all boils down to this one simple but incredibly powerful idea that Einstein wanted to capture with math. On one side of the equation, you've got a way to measure the curvature of spacetime. And on the other side, you've got the thing that's causing that curvature, the source of the gravity. That's it. That's the core logic we're going to keep coming back to.
So, you've got this universe-changing idea. Now what? How in the world do you write that down? How do you capture something so immense in the language of mathematics?
Well, in 1915, Einstein did exactly that. He unveiled a set of equations that perfectly expressed this relationship. And this wasn't some simple formula you learn in high school. Nope. It's a super compact way of writing 10 deeply interconnected equations that are, famously difficult to solve. But their real genius isn't how complicated they are, it's in what they represent.
And here it is, in all its glory. I know. At first glance, it looks incredibly intimidating, right? Just a scramble of Greek letters and symbols. But don't worry, we're not going to try and solve it. Our goal here is just to understand what each part means. We're going to take it apart piece by piece.
Let's start on the left side of that equals sign. This is the measure of curvature part of Einstein's big idea. This is the math that tells us all about the geometry of spacetime.
The big star on the left side is this thing called the Einstein tensor, that g mu nu symbol. Now, tensor is a fancy word, but you can just think of it as a machine, a mathematical tool that can describe different physical things at every single point in space and time. The Einstein tensor's job is to precisely measure the curvature at any point, and it does it in this really clever way that makes sure a fundamental law of the universe, the conservation of energy, is never, ever broken.
And this Einstein tensor isn't just one thing. It's actually built from a few smaller parts that all work together. The most basic piece is the metric tensor. You can think of it like a universal rulebook for measuring distances in this weird, warped 4D landscape. The other pieces then use that rulebook to figure out things like how volume changes or what the overall curvature is at a single point. Put them all together, and you get a complete geometric picture of space-time.
Okay, so if the left side is the shape of space-time, what's actually deciding that shape? For that, we got to jump over the equal sign and look at the right side of the equation. This is the source of gravity part.
Over here, we meet another tensor. This one is T mu nu, the stress-energy tensor. And its job is simple. Describe every single thing in the universe that can be a source of gravity. And trust me, it's a lot more than just the obvious stuff.
And this, right here, is what makes general relativity so mind-bendingly powerful. It's not just mass that bends spacetime. It's everything. The stress-energy tensor takes into account the density of energy, the momentum of stuff moving through space, and even things like pressure. This is why the theory predicted that even light, which has no mass, would have its path bent by gravity as it passes a star like our sun. That was a shocking idea at the time, but it was proven true, and it was a huge win for Einstein. This tensor is basically the ultimate description of all the stuff in the universe. Okay, now for the grand finale. We've seen the two sides of the puzzle. We have the geometry of space-time on the left and all the matter and energy on the right. Let's put them together and see the magic happen.
This is the great cosmic dialogue. Think about it like this. On the right, you have all the actors in the universe, all the matter and energy.
described by the stress-energy tensor. And what they do is tell the cosmic stage, space-time itself, over on the left, how to bend and curve. The equal sign is the link between them. The contents of the universe literally dictates its shape.
And boom, we are right back where we started. The Einstein field equations are the perfect mathematical translation of this idea. The geometry of spacetime is directly tied to the presence of matter and energy. One side equals the other.
You know, this whole thing has been summed up so perfectly, it's beautiful. It's a two-way street. Matter and energy tell spacetime how to curve, and in return, the curvature of spacetime tells matter how to move. It's this incredible, dynamic interplay. It's the dance that governs the entire cosmos.
For over 100 years now, this equation has passed every single test we've thrown at it. It predicted black holes, it predicted gravitational waves, things we're only just now able to observe. But we know it's probably not the final word. It doesn't quite play nice with the weirdness of the quantum world. So the question that drives physics today is, what comes next? What new equation will finally unite the universe of the very large with the universe of the very small and reveal an even deeper truth about how everything works?